All right. In this module, we're going to continue talking about nucleation and look at the free energy of nucleation. All right. So, again, we're talking about this concept of free energy, which you don't have to know everything about this. This is something that you learn more about in thermodynamics. But in a nutshell, it basically tells us what is favorable or what is not favorable. So basically, a negative value uh, means that something is likely to occur. A positive, it is not likely to occur. So that's the basics of it. Um, so when we look at nucleation, we're actually going to look at two different terms that happen when we form a new phase. So the first one is this positive term uh, in red here, the red dashed, and this is related to the surface free energy. And what this is it's the surface energy, it's the surface area that's created between the solid and the liquid interface. And so this takes energy. This is not favorable to form a new boundary between solid and liquid. And so that's why this is positive. It kind of what we say is destabilizes the nuclei. And so this will increase as the radius of the particle increases, right? Because the surface energy will decrease. The surface area will increase, and therefore the energy will increase. So that's what the red curve is showing us. And so this can be related to the surface free energy can be related to 4 pi, the radius squared of the particle multiplied by the surface tension um, between these interfaces. The other part that is stabilizing or favorable to the system is what we call the volume or bulk free energy. And so this is the free energy behind the formation of this new solid phase, which again we know as favorable based on the fact that we're below the equilibrium temperature. And so this is related to the radius cubed because of volume, right? So this is basically a volume term multiplied by the free energy per volume. And so in this case, the term decreases, becomes more and more negative as the radius increases. But as we know, this is r cubed and this is r squared. So this is going to do this more rapidly than the surface term. So when we look at the combination of both terms, which gives us the total free energy of the system, we're going to add those two terms together, right? And so when we do that, because this r cubed term decreases at a faster rate than the r squared term increases, what we see is that initially the total free energy increases, becomes less favorable, but at a certain point when this volume term takes over, then we see it start to decrease and eventually goes negative. And so we see here that this is a maximum. So this is kind of a critical value in this scenario because this is the total amount of free energy that we would have to put into the system for this to occur. So basically what this is showing us is that this is a critical point. So we call this delta G star, because what happens is once the nuclei reaches the radius here, corresponding to this value, we call it R star. So this is R star because that's the maximum amount that we have to put into the system. So for radii less than r star, the nuclei is likely to it is just as likely to shrink as it is to grow. However, when the radius equals that r star or greater, then the nuclei is said to be stable and it will continue to grow to reduce the free energy of the system. So that's why we call this kind of the critical nucleus, because that's where it becomes stable. Below that, it's also likely to go back to liquid. So what we have to do is we basically have to supply delta G stars worth of energy to the nuclei before it becomes stable. So that's why we call it a critical value. And so if we take the terms for volume and surface and add them together, we saw that we had that, and we can actually solve for this maximum and solve for R star by looking for the maximum of this equation. And if we solve for that, we see that the critical radius R star is equal to minus 2 times the surface tension or surface free energy multiplied by the melting temperature divided by the latent heat of solidification, so the enthalpy, multiplied by the supercooling, so delta T. And so this allows us to calculate the R star for this system. And what we see is that it's going to be a function, an inverse function of the delta T, the supercooling term. A couple other notes to mention here. So enthalpy and surface energy are weakly dependent on this temperature, but not as much as the R star. So it's just a couple, these can change with temperature, but for the most part, they're only weakly dependent. So what we see is that R star will decrease as supercooling increases, right? So the temperature decreases overall. So the size of the critical nuclei becomes smaller with decreasing temperature or increasing delta T. And so if you're wondering some approximate values here, what these values tend to be. So for typical degrees of supercooling, the critical radius is about 10 nanometers, right? So that's when it becomes critical. So about 10 nanometers. All right, so along with that, we can calculate the delta G star, and that's when we reach the critical radius, right? The energy value there, and this has a similar dependence, right? It's just the form of it's different, but it has the same components. We have the gamma, which is the surface free energy. We have melting temperature, the latent heat of solidification, delta HF, and then the degree of supercooling, and that's squared. So different form, but same variables in this case. And what we see is that the barrier for forming a nuclei decreases with decreasing temperature, right? That's what we saw. That's what we kind of said in general happens. Because this is again the driving force. But this allows us to put some numbers behind these general ideas.